Hey guys, Miss Barber here with section 6.1 in geometry, finding angle measures and polygons. This could be in either chapter 1 as an introduction to polygons or in chapter 6, which is the whole chapter related to polygons and quadrilaterals, which is a type of polygon. So our learning target today is to find angle measures and polygons and classify these polygons based off of sides and angles and other properties. So for a polygon, a polygon just is a shape made up of segments, and those segments in a polygon are called a side. So you'll see here, this is a side, it's a segment. The segments all intersect at specific points called vertex, or plural vertices. So here's a vertex, that's where the sides intersect. You can also connect vertices that are not adjacent, not exactly next to each other, and those are called diagonals. So diagonals is when you can connect non-adjacent vertices. So for polygons, to name them, the smallest polygon you can have is a triangle. That's the smallest way you can connect three sides into a closed figure. Four-sided polygons are called quadrilaterals. 5 is pentagon. 6 is hexagon. 7 is heptagon. 8 is octagon. Think of an octopus, 8 legs or tentacles. 9 is nonagon. 10 is decagon. And then anything above n or 10 is called an n-gon. So if there's 12 sides, you would just call it or 12-gon. There's actually a name for 12 sides that sometimes is used. So let's go ahead and write that down. 12 sides also is called a dodecagon. Do is 2 and deca is 10. So 10 and 2 is 12. So dodecagon is another way to call a polygon with 12 sides. If you have 25 sides, it would just be called a 25-gon. There's actually a really fun polygon song that is on YouTube that I recommend you looking up. That'll help you to remember those. It is important that you do know the polygons' names and how many sides that those names indicate. So a regular polygon is a polygon where all sides and angles are congruent. So all sides have to be the same and all angles have to be the same. So a regular polygon looks regular. It looks like a normal shape that you probably saw as a child when you played with those puzzle games and things like that. A polygon is convex if all the diagonals lie in the interior, and concave if you draw a diagonal and one of them's outside. It's usually easy to see a concave polygon because one of the sides looks like it's caving in. So in order to be a regular polygon, like we said, all sides have to be congruent. Another word for all sides being congruent is called equilateral. So equilateral means all sides are congruent. Equiangular, and no, that's not a mistypo. There is no L in equiangular. Equiangular means all angles are congruent. So if all sides are congruent and all angles are congruent, then the polygon is regular. If it's regular, it also has to be convex. It's impossible to draw a regular concave polygon because then all the angles would not be the same. So here are some pictures to kind of help you visualize this. So here we have a regular polygon. It is regular. Notice all 4 sides have the same tick mark, and we also have 4 right angles. And it's convex. I could draw diagonals in, and they stay on the inside. It's not caving in anywhere. For this middle polygon, it is irregular. It's irregular because although all 4 sides are the same, not all 4 angles are the same. Opposite angles are the same. So my blue angles are the same and my yellow angles are the same, but all 4 are not. So it cannot be regular. So we can just call that irregular. All 4 sides are the same, so we could call it equilateral. And again, it's convex. Nothing's caving in. I draw diagonals, they stay inside. This last one here is irregular. Notice we have sides of different lengths and we have angles of different measure. So no, it's not equilateral or equiangular. It's also concave. It is caving in right here. If I draw a diagonal here through the top, it would stay on the outside of the polygon. So it is concave. So example 1 here, tell whether each is a polygon. If it is, name it by its number of sides. So number 1, is it a polygon? I see all line segments intersecting at vertices. It's a polygon, so how many sides does it have? I count 5, so yes, it is a polygon, and it's a pentagon. 5 sides is a pentagon, just like the building in Washington, D.C. Number 2, is this a polygon? Again, I see a bunch of line segments intersecting at vertices. Yes, it's caving in right here, but that doesn't affect it being a polygon. It's just not a convex polygon. It's concave, but it's still a polygon, so yes. And I counted the number of sides, and I see that there's 7 sides. 7 sides makes it a heptagon. Then number 3, is this a polygon? Remember, our sides have to be line segments. Hopefully you see here, definitely not a line segment. That's a curve. So we cannot have curves in polygons. So no, this is not a polygon. You're not allowed to have curves. So no curves in polygons. So yes, a circle is not a polygon. It is a shape, but not a polygon. Now let's determine if it's equilateral, equiangular, regular, irregular, and then concave or convex. Number 4, is this equilateral? So you ask yourself for number 4, are all 4 sides the same? They're not, so it is not equilateral. This top side is different. Are all 4 angles the same? They're not. The top and the bottom ones are different. So here is different from here. So it cannot be regular because it's not equilateral, equiangular, so it's irregular. I don't see it caving in anywhere. I draw diagonals, they stay inside, so it is convex. Number 5, is it equilateral? I see 3 sides that are all the same, so yes, it's equilateral. I'm just going to write EL for equilateral. Is it equiangular? Again, I see 3 equal angles. So yes, it's also equiangular. I'm just going to write EA for that. Because it's both of these, it has to be regular. That's the definition. So it's not irregular, it's regular. And again, convex. Number 6. Go ahead, try this one on your own. Again, check it against the key. Ask yourself, are all sides the same? Are all angles the same? Does it cave in anywhere? Can you draw a diagonal on the outside? All right, so that's it for classifying polygons. Now, what about doing some math related to polygons? So here are lots of polygon angle formulas you need to know. In all of these formulas, n stands for the number of sides, which is the same thing as the number of angles. Triangles have 3 sides and 3 angles, so it works for both. The sum of the interior angles. That means inside angles. So for all inside angles, we're going to use this formula of n minus 2 times 180. So all the inside angles, if we take the number of sides and minus 2 from it, and then times it by 180, that'll tell us what all of the angles on the inside have to add up to. For one single interior angle, so usually we use the word single or one, or maybe each. If it says each interior angle, now it has to be regular because we don't really know if they're not all the same. But if they're all the same, we can find out what just one is. It's the exact same formula here as the top, the n minus 2 times 180. So number of sides minus 2 times 180. Except you have to divide by n, or the number of sides, because the number of angles that exist in the polygon, divide it by that, and it'll tell you what 1 is. The sum of the exterior would be all the outside angles. And it's always going to be 360. It doesn't matter how many sides a polygon has. A quadrilateral with 4 sides, the exterior angles will add up to 360. A dodecagon with 12 sides, its exterior angles will add up to 360. So that does not change. So for a single or one or each exterior angle, you're going to do the same thing. You're going to take the sum of the exterior, which in this case is 360. So it's going to be 360 now, but then you're going to divide it by n, the number of angles. So that will tell you what just one is. So these 4 formulas, as long as you know when to apply them, you should be able to do each one of these problems just using one of these formulas. So example 2, find the sum of the measures of the interior angles of the following polygon. So find the sum of the interior. That tells me I'm going to be using that first equation. So I'm going to be using our formula, n minus 2 times 180. So all I really need to know is what n is, the number of sides. So in letter A, n is 6. This is a hexagon. There are 6 sides. So I'm just going to apply this formula. 6 minus 2 times 180. Order of operations would say I have to do what's in parentheses first. So 6 minus 2 is 4. So I'm going to do 4 times 180. So the sum, all 6 of these interior angles added together will be 120 degrees. So each one of these interior angles, when I add them together, will give me 720. So letter B and C are the same. We'll try B again together, and then you can try C on your own, checking against the key. So again, all I need to know is what n is. Nonagon means 9 sides, so n is going to be equal to 9. So I'm going to do n minus 2, which is 9 minus 2 times 180. 9 minus 2 is 7, so 7 times 180 is 1,260. So that's what your answer is going to be for letter B. Pause the video, try C, and then check your answer with the key. All right, now, example 3. Find one interior and one exterior angle. So I see one interior and I think, okay, one interior angle, I'm going to be using this single interior angle formula. Then for one exterior angle, I'm going to be using this single exterior, number 4, the 4th equation up there, the 4th formula for each. So let's go ahead and try this. A quadrilateral. I just need to know what n is, so n is 4. Quadrilateral is 4 sides. So for interior, the formula is n minus 2, so 4 minus 2 times 180 divided by the number of sides or the number of angles, which is 4. Putting that in the calculator and you get 90. Or solving it in your head, whatever. So let's do the exact same thing for exterior using the exterior formula. The exterior formula is just 360 divided by n, which is 4. Well, 360 divided by 4 is 90. So you might be thinking to yourself, interior was 90 and exterior was 90. Are they always going to be the same? And if you're thinking, I don't know, maybe, maybe not, well, let's try another one. Let's try letter B and see where that takes us. So letter B, this is a pentagon, so n is 5. There are 5 sides. So let's do interior first. Interior is going to be 5 minus 2 times 180 divided by 5. So 3 times 180 divided by 5, that's giving me 108. Sorry for my poor handwriting. That is 108. All right, now let's try the exterior angle. So 360 divided by 5 for the 5 sides or 5 angles. 360 divided by 5 is 72. So now notice, obviously, not the same, right? One is 108, one is 72. So they're not the same as they were in letter A. But you should notice something. There is a relationship between them. 90 plus 90 is 180 degrees. So the interior and the exterior of my first problem are supplementary. Same thing in letter B, 108 and 72 are supplementary. They add to 180. And that's not a coincidence by any means. Let's use this pentagon here as a picture to help us. If I extend out my side, my interior angle is going to be in here. Clearly, it's an obtuse angle, so 108 makes perfect sense for what that's going to be. My exterior angle is going to be this angle on the outside that's adjacent and a linear pair to the inside angle. So it only makes sense as a linear pair that they're going to be supplementary. So do you have to apply the formula for both the interior and the exterior? Absolutely not. You're more than welcome to just find one of the two and subtract from 180 to find the second one. So choose a method, whatever you would like for letter C, and again, check your answer against the key. Example 4. Example 4 asks us to find that given the sum of the measures of the interior angles, classify the polygon by the number of sides. So it's the exact opposite of what we did in example 2. Instead of them telling us the number of sides and us finding the sum, they're giving us the sum and we're asked to find the number of sides. So we're going to apply the formula in reverse. So now the sum, 2,700, is equal to my formula of n minus 2 times 180. So I'm now tasked with solving an equation. Order of operations says I should divide by 180 first. So I'm going to do that. So step 1 is to divide. So you're dividing by 180 first. The 180s cancel. And you're left with 15 equals n minus 2. You don't need to write the parentheses anymore. So step 2, we need to add 2 to both sides. That's the big mistake people make. They just get so excited once they divide by 180, they forget to add 2. So add 2, add 2. So we're going to be left with, and I'm sorry I'm running out of room here, we're going to be left with a 17-sided figure or a 17-gon. So it's going to have 17 sides. Go ahead and try letter B on your own and then check your answer on the key. All right, last example is example 5. Find the unknown interior exterior angles. So now we're given a picture. And in these pictures, we're either given interior or exterior angles, and we have to determine what the missing value is, either A or X. The first question you have to ask yourself always for these types of problems is, are these interior inside angles or exterior outside angles? Letter A, these are interior angles. That's important because we still have to apply one of the formulas above. Because we have to determine, this is the sum of the interior. So the sum of the interior is up here at the top. We're going to have to use this n minus 2 times 180 to determine what all of these angles have to add up to. So looking here, I see that there's 6 angles or 6 sides. So I know I have to do 6 minus 2 times 180 to find out what all these angles are going to add up to. Well, that, when you work it out, is 720. So all 6 of these angles, when I add them together into the same equation, I know they're going to add to 720. Well, adding up all of those, you get to 24A. So 24A is equal to 720. So we can divide by 24. And A is going to be 30. So then that's just your answer. It said find the value of A. So again, what's tricky is I needed to know first that they're interior angles so I could apply the interior formula. In letter B looking, I see all of these angles are on the outside, so these are exterior angles. Looking above, exterior angles, the sum of exterior angles, it's always 360. It doesn't matter how many sides there are. So I don't have to go through and do any little special equation to figure out what these are all going to add up to. I know that they have to add up to 360. Most people just want to always make them add to 360 because it just seems obvious, but that's not true. Interior angles can add up to all sorts of things, not just 360. Only outside ones are. So if I add up all of these, I'm left with x plus 332 equals 360. So I can subtract 332 from both sides, and I'm left with x equaling 28 degrees. Yep. All right, so again, biggest thing for these types of problems like in example 5 is determining if you're using an interior formula or the exterior, so you can go ahead and set them all to 360. So make sure you're careful and watch out for that. That's it for lesson 6.1. This was Miss Barbara. I hope you all